Hello everybody, and welcome to the stream. It's been quite a while since I've done one of these streams, so welcome to all of you guys. Thank you for showing up. And today we're just going to sort of tackle a variety of things. So one of the main things I want to tackle is a little bit of refactoring, resolving some of the long-standing issues that have been out there. And we're actually going to take a look at our first memory allocator today. It's going to be a simple one, but we want to get that in place and adjust our memory model a little bit for our application state. And there's a couple of other things that I want to get to if we have the time. We'll see how this goes. So, cool. So first and foremost, before we jump into this, I want to go ahead and really quickly just thank our partners and supporters. So you guys are the ones who are the members of the channel, as well as the Patreon supporters. So thank you guys for that. Without you guys, this definitely would not be possible. So, all right, without any further ado, let's go ahead and crank up the old refactor tractor and get this going. So, I'm actually going to start off with a view here of the desktop and camera. Let me know what you guys think. If you want me to hide the camera, I can do that, or if you want me to leave it on, I can leave it on. We'll try it this way first and see how it goes. Okay, so I actually have a checklist of things here that I want to handle today, and Raz, I don't know if you're on, but this first one is for you, buddy. So the very first thing that I want to address is actually the way that we are handling Booleans. So as a lot of you probably know, or may not know, Booleans in C aren't really a thing by default. So we are basically just using an 8-bit integer. And I've actually decided that maybe that's not the best way to go. I think I'm just going to use the sort of underscore Boolean type instead. Because it's a little bit more specific. And so I'm going to swap this out underneath the hood to use that instead. So that, thankfully, is actually a pretty straightforward change. That is going to be here in our defines. And instead of type defing character, it's just going to be underscore bool. And let's go ahead and just build that and make sure that that didn't break anything. Cool. I'm going to go ahead and run this. And we are good to go. So nothing changed there. Okay, cool. So that's the first item. The next thing I want to address is we sort of have this uppercase true and false here. And this is sort of an old school habit of mine, but I kind of don't really like it anymore stylistically. So I actually kind of want to go through and replace all these uppercase versions with lowercase versions. That way it'll be a little bit more standard, I guess you could say. So I'm just going to do a find and replace on all files. Case sensitive, probably whole word too. And replace it with a lowercase version of that. Again, these are relatively small changes, but ones that have been bothering me for a while. So go ahead and knock these out. Okay. Go ahead and do that. And we should be good to go there. I'm going to go ahead and build again. Hey, Raz. Welcome. I don't know if you happened to hop in, but I went ahead and did your Boolean type here. So I don't know if you were on the stream when I did that, but you should be happy about that. Okay, so we built successfully. Just want to run real quick just to verify. And we're all good. Okay, so that's that. The next thing that I want to address is we're actually making use of variable length arrays in a few places in the code base. And that's not something that I really want to do anymore. It's not something that's particularly portable. And I think I'm just going to remove those anywhere that they exist in the code base. So the first way that I'm going to do that is I'm actually going to go into our build files and disable VLAs. Well, not disable, I guess, but warn anytime they are used. And that will keep us from actually using those going forward. So the way that I'm going to do that is I'm going to go into our compiler flags, and I'm just going to whenever we have a VLA. And I'm just going to do that sort of across the board here. And that should make the portability of this a little bit better, because VLAs are kind of weird, and they are not always they're not handled the same by every compiler. So Clang has them on by default, so I'm actually just going to throw an error anytime we have one. And so this time when I build, it should. I'm actually just going to clean and build. Yeah, so now we get some errors. So we'll just have to go and clean these things up, get rid of these. So there's not too many of them, thankfully. So let's see. So the first one is in our logical device, and I actually think this is where most of them are, is actually in the device, if I remember correctly. I don't think I widely used them. Yeah, it looks like they're all in the device. So what I'm going to do is, let me see, let me look at my notes here. We have, I think I just hard-coded that number to 32, if I remember correctly. Yeah. So I'm just going to hard-code this to 32, because technically that's the maximum number of indices we can have, if I recall correctly. And so basically I'm just going to go through here anywhere there's this index count being used as the size of an array, and I'm just going to replace that with 32. And let's see. This will still work, by the way, because we are never going to have more entries than this, but we're still only iterating over the index count. So when we're actually setting these things up, we're still only actually setting the ones that we need to set. And yes, technically it's a little bit of a waste of memory, but by the time we hand it over to Vulkan, since this is all done on the stack, it won't matter anyways. So that's the first. And the physical device count is the second one. And if I recall correctly, that one has a limitation as well as to how many physical devices can actually be returned from that. I think the way that I'm going to handle this one is I'm probably going to go ahead and do the same thing and just use 32. So I'm going to put in here just a max device count, and it's going to be a const. And I'll just use that instead. And then get rid of this guy. I believe there was one more down here, which is the Q families. And this is where we are checking to see if our device meets requirements. So I'm actually just going to really quickly, I think I used 32 for that one as well. Yes, I did. Okay. So I'm going to go ahead and clean again and rebuild. And it looks like there is also one in Vulkan render pass. That is, I think that's just because it's not const. Whoops, caps lock. So I think if I change that to const, we'll be fine. Okay, and actually just to be safe, I'm going to clean and rebuild. Hi Giuseppe, welcome to the stream. I hope I pronounced that correctly. Okay, so let's go ahead and run this real quick. and it looks like we are good. We have not found any validation errors or anything like that. So that is good to go. Okay. So the next thing that I want to quickly address is, and this is more preference than anything else, but it is a relatively small thing, is in the launch JSON, we are actually doing this new external window for the console. And that is what makes that new window pop up instead of going here to the terminal. And that's kind of a pain in the butt when I'm doing these videos because I have to drag both windows up. So I'm actually going to switch that to just use the terminal in here instead. For those of you who are using a different setup, you may not want to do this, but I'm going to go ahead and change it in these properties just so that going forward it works a little bit easier for me. So if I recall correctly, I need to use integrated terminal instead of new external window. So I'll go ahead and launch. And yeah, now you guys can see that I get my log here. So that's just a little bit easier to work with. So that was another change. Okay, so that is most of the simple changes out of the way. Some of the more complex changes, or I should say widespread changes, are coming up next. So I actually have a couple things here. I think the next thing I'm going to handle is a bug that I found in the swap chain. There is an assumption being made that we probably should fix. So it is around line, I think it was like 93. Yeah, here it is actually. It's right here. So right here, we are actually hard coding the max frames in flight to 2, which is not ideal because if you aren't using triple buffering, this won't be the case. You'll only have one max frame in flight. So what we should actually do is take the image count and subtract 1 from it, and that should be our max frames in flight. So I'm actually going to take this from here, and we scroll down a little bit until we get our actual image count, which is here. And right below this, I'm going to set it to image count -1. And that way, no matter what setup we have, this number should always be correct. Okay. And again, just as a sanity check, I'm going to build and run. And we're not getting any sort of errors there, and this runs. So we're good. Okay. So let me read some of the comments here. I don't know if you're planning on addressing this today or if you've even noticed so far as I understand your event system overwrites the listener every time you register a new listener for the same event type. Yeah, so I did notice that. I may come back and fix that today. We'll see if we have time. That is on my list. If not, I'll fix it in the future past. But yeah, I did notice that. It's not ideal. But yeah, thank you for pointing that out. So I think probably the next thing I'm going to work on is an issue that I found with the input. So right now, actually, if I launch this, we actually get the same code output to the console, no matter whether you press left shift, left control, right control, and the same is true for the alt keys, right? And they're putting out these sort of rubbish values here because ASCII doesn't know what to make of it, and that's fine. But the problem is we're not actually differentiating between the two. And I noticed this from an issue that Jad brought up with the way that they were mapped, and we were sort of using the Windows old school menu definition for the key, and I sort of want to get away from that and fix the issues around that. So this one begins with a check. So if we look here, we have in our input H, we have defined L menu and R menu, and these things are technically the alt keys. However, there's also this this sort of context menu key that is on the keyboard next to the Windows button, and I'm not going to necessarily map that, but the menu kind of can get confused with that. So I'm going to rename these to alt. And then I'll go ahead and map these correctly at the platform layer. So in Win32, we are going to look at the WM key down set of cases, key down, key up set of cases. And we're going to put some additional filtering in here to determine if we actually are pressing the left or the right Alt or Shift or Control key. Because right now, basically this event only passes us whether or not we're pressing a Control key or a Shift key or a Alt key. It doesn't actually tell us which one. So what we're going to have to do is actually look at the state of that and of those individual keys, rather, when we receive that event to actually determine which one is truly being pressed. So if our wparam is equal to, I think it was it wparam? Yeah, vk menu, which this is what Windows calls Alt, by the way. So in other words, if we get a key press for Alt, this is basically just telling us Alt has been pressed, doesn't tell us which one. So we're going to have to check the key state of the left and right Alt. So we can say if, and then call a method called get key state. And to this we can pass the virtual key code, which is going to be vk. We'll do the right first, so we'll say R menu. Right, so if the key state of that, and then we AND that with 0x 0, was it 0800? No, I think it was 8000. You know what, let me double check that because I don't recall if that is what I actually need. So let me go ahead and consult the MSDN documentation on that. So let's see. So this is the page that I originally checked, I believe. Yeah, here it is. Okay, so here is the keyboard state, and yes, it looks like I got that right. So for some reason you have to AND this with 0x8000 in order to detect that a key is down. So instead of just doing vk menu, I'm actually doing this right here, which is for the R menu, right? So I'm basically doing this exact same thing, and then this will tell me that the right Alt key is down, and then I'll do the same check for the left Alt key. So in this case, what I'm going to wind up doing is just overriding the key that is set from being this vk menu to equaling key right Alt. Right, and that just sort of overrides that. And then I'm also going to check, otherwise if it's not R menu, then we'll check the L menu, and it changes to L Alt. Right, and this will just tell us which one of these things is actually being pressed. Okay, so let's see, let's just look back at the comments real quick. How long do you plan on streaming today? Maybe an hour or two, we'll see. Not too long, but yeah, I'm thinking an hour or two. There seems to be a virtual key code for every key on the keyboard. That is true. However, the virtual keys are a little bit different between OSs. Linux handles it a little bit different than Windows. So unfortunately, we'll have to handle this a little bit differently for each, but I guess that's not the end of the world. I actually technically like the Linux implementation a little bit better. And then, oh, hey, there's Jad. So welcome, Jad. Cool. All right. So this is for the Alt key. So I'm just going to put in here. I can't type today, apparently. Alt key. And I'm going to do the same for the control key. So actually I'll do shift next. So if we've pressed the shift key, then we need to check the right shift and remap that if that's being pressed. Same thing goes for left shift. Wow, I really can't type today apparently. Shift. All right, so it's the same exact process, we're just doing it for shift, and then of course we're also going to do that for control as well. So if a control key is pressed, then we'll check to see if right control is pressed, and remap that. L control and remap that. Okay. So now that these are mapped, we probably ought to have a way to verify this as opposed to outputting these sort of crappy codes here. I'm going to put something temporary in the input layer so that we can actually tell whether the left or the right was actually pressed on that side instead of this. So let me go into our inputs.c, and when we are doing the process key, that's probably where we're going to wind up putting this. I think that makes the most sense because in our platform layer we are calling input process key. So yeah, that's actually where I'm going to put it. And in the inputs, let's see. I think all I'm going to wind up doing is checking the key to say if key equals key, we'll do left alt first. Then we'll say k info left alt pressed. Okay, and then I'm just going to copy pasta this for right. And then I'm going to copy pasta this whole thing for, we'll do control next. And set control, CTRL. Okay, and finally shift. Just to verify that this is working. Okay. Cool. So let's go ahead and build that. wparam holds all the key codes. Mouse virtual codes don't seem to work though. I wonder how you'll make Linux and Windows virtual key codes work together. So are you talking about the mapping between those two and getting them to sort of output consistently? Is that what you mean, Raz? Let's run this. So now if I press, oh, it's not working for some reason. What did I forget? Input process key. What did I forget? Maybe I just need to rebuild the whole thing. Shouldn't have to, but speaking of which, that's another thing I need to point out. Small change that I sort of snuck into the repo while I'm at it. So if we look at these make files, you'll note that there's this -md that's been added to the compiler flags, and then down here at the bottom we have this include obj files.d. So basically what that does is it generates dependency files, so that way when we change a header we don't have to recompile or clean and recompile the whole thing in theory, it should be able to detect that that header file is a dependency and recompile. So it should solve a lot of those issues. I know a few of you guys brought that up in comments, I think on the Discord server as well. So just wanted to point out that I snuck that change in a while ago, but that is what that does. So let me see, does this, might help if I had the actual right window. No. Strange. It doesn't seem to be working the way that I thought that it should. So, what did I miss here? Let's try separating these out. Shouldn't make a difference, but oh, you're wondering how they would map. Okay, Raz, I'll show you that here in a second. I do actually have a mapping for all of the key codes in Linux to map to the ones that Windows uses. So I'm technically using the Windows ones because they line up nicely with sort of the ASCII key codes. And so I'm using those ones by default and then remapping for other platforms to everything that's listed here. So these are actually mostly taken directly from Windows.h because these key codes line up nicely, and I'm just remapping to these ones. But I've got these defined here so that I don't have to have Windows H sort of defined everywhere. So better off being in a switch. Yeah, switch statement probably would be better. It's technically speaking, it's kind of the same thing. If it's just a bunch of else ifs, you're still going to hit one of those only anyway. So it technically winds up being the same thing, just in less lines of code because you don't have to have a break every single time. So it's preference, really. I could do it in a switch. I could do it this way. It doesn't really matter because these are, well, I guess technically you're talking about this section being in a switch or the other section being a switch? Godbolt has some interesting result with switch and if. Yeah, I should probably do that just to see what the generated assembly is. That's definitely an interesting point. I don't know if I necessarily want to dive down that rabbit hole. I don't know if this was the section you were talking about though. If this is the section you're talking about, maybe a switch would be better. But that's the thing. Like, you have to check this and then check this. So I could make this part a switch here, but you're not really going to gain anything from that, if that's what you're talking about. Anyway, so let's go ahead and see if we can figure out what is going on here, because I have a feeling I just probably... So I'm reassigning the key here if it falls into any of these. Should just... Why would that not pick that up, I wonder? This looks fine. Maybe it's my process key logic that's wrong. Pressed. Yeah, I'll have to see what it's actually passing through. So left shift, so we should technically get left shift pressed. Am I crazy, or was that not working a minute ago? All right, let me just continue and try hitting a couple of other keys here. So where did my window go? It only seems to work once. Maybe wrong window. That was what I thought initially, but... Oh, I know what's happening. Okay. That's because I had the... Yeah, you're right. It was the wrong window. Because I had the debug console open, and that only captures info and debug there. It's not actually output. Okay, it's actually working correctly. I hate when that happens. Okay, so I think we are good here. No, it's actually not working. Strange. Let me actually try switching this back to the other console and see if it works there. So we get the left shift pressed, but it only happens once. It only happens once for each control. That is bizarre. Why do you not use designated struct initialization? I do, actually. I just don't necessarily use it everywhere. Hello, just came across to your videos. How long have you been programming? Programming in general? God, how long has it been? Probably better part of 20 some odd years. It's most likely we're the first where clause in process input. Yeah, that's what I'm wondering too. I'm going to breakpoint here again just to see what is going on. So the first time I hit Alt, it comes through. So if I refocus the window and I hit it again, yeah, it's not even getting the key press at all beyond the first time. So that time it works. Interesting, it's not even processing the input key past the first time I press it. That is interesting. So it's not even hitting the breakpoint after the first time that I do this, which is interesting. Do you ever set the key not being pressed after it is released? Yes, the key up event does that. So that is, I don't think what it is. The first where clause says only go ahead if not pressed. Oh, are you talking in here? Oh, right. I see what you're saying. It's here. But it should... Oh, you know what? Yeah, I think I know what's happening. I think I know what it is. It is... Well, actually... Because this handles both key down and key up, right? So this should fire this event in both cases. But this is in the wrong spot. So I think it's actually working. I think it just needs to probably be here. I'll bet that's what it is. Of course, this is technically going to show now every time I press it and release it, but I think that is what it's going to be. Get rid of my breakpoints. Okay. Yep, that's what it is. Okay. All right, so that works. I just had it in the wrong spot. That's the kind of crap that happens when you are programming live, unfortunately. And I've probably written this 1,000 times before now, and of course I've never run into that issue before, but it is what it is. Anyway, so that is how we're going to detect that. Now I'm going to actually cheat a little bit, and I'm going to go ahead and fix the Linux code. Even though we can't technically test it now, the fix for this is actually pretty simple because there's just really one small issue here. So in Linux, we're actually checking, we actually get separate events for the left and right shift and left and right control. And for some reason, I only tied the Alt to just the menu instead of looking at the left and right, which is not right. So this is a pretty minor fix. And actually I have in my notes a quick fix for this. It's just to clobber this and replace it with that. And so we've literally just remapped these codes. So Raz, you were wondering how I go ahead and map those things over. Linux actually has this, the Linux layer has this translate key code. So I take the X key code here and output it to one that we recognize, right? Because these numbers are vastly different. So that's how we handle that. When we get to the Mac platform, we'll handle it that way there as well. Obviously, for now, we're just using GLFW on there. But once we do the official Mac port, we'll set that up as well. Okay, so that took a little bit longer than I wanted, but that is pretty much all there is having to do with input, I believe. So those are all the quick things. The next thing that I want to jump into is I want to talk about our current state and the way that that's held across a lot of our sort of subsystems and whatnot. And I want to refactor how that works because a lot of that stuff's being held in the stack right now, and that is not great. I did that as sort of a temporary stopgap to keep things separate until I actually implement a more global state, as it were. But I think it's time that we go ahead and switch over to a new model. So before I do that, let me just tie up any questions. What does key state actually return for it to make the return true when you bitwise it with 0x8000? I don't remember off the top of my head. That is what they suggested to do in here. I don't completely recall why that is. I think it's because only certain of the bits actually are set. Let's see. Returns a set of bit flags. Yeah, there it is. So we have to check against this, basically. And that contains the bit flag that tests whether or not the key is currently pressed. So I don't know why they did it that way. I don't know why they don't have like a defined constant or something like that. It'd be a little easier to understand. I may go back and actually put one because I'm not a huge fan of magic numbers like this, but yeah, that's why. Hope that makes sense. Okay. Let me close some of these things here. It removes all the state not relevant to the key being pressed, you believe. I'm not sure what you mean by that. Okay, I'm going to move on, and then I'll jump back to that. Okay, so our application code here, our startup is, it's going to get sort of messy if we don't stop and think for a minute about how some of this stuff is stored, right? So right now, a lot of these things, like events, for example, if we take a look at the initialization, we're actually storing its state on the stack here statically. And this is not great, right? Like this is going to be pretty heavy, especially when we get to some of our other systems that we have in place. And it's not really the way I want to go forward. So the way that I'm going to get away from this is we're going to have sort of a an application state that provides state to each one of these subsystems. And we are going to allocate memory for that up front. And then we are going to provide a pointer to the state that this then populates with whatever state information that it needs. What do I mean by that? So basically, I want to have our application state here contain things similar to this platform state, but basically a bunch of memory blocks that can be provided to each one of these individual subsystems. And the subsystem should tell us how much memory it needs. We can allocate that from within the application, and then pass that allocated memory over to the subsystem so it doesn't have to worry about it. And I'm going to do that because I want to start doing things in a way where it doesn't have to, things don't have to have things, let me reword that, so that the individual subsystems do not have to allocate memory on their own. I want to start getting rid of dynamic allocations wherever possible. And we only basically want to do dynamic allocations when we first start the engine up. And we want to sort of set up arenas of memory that we can then allocate from so that we don't have to call malloc all over the place, because that's slow and we don't want to be doing that. We want to basically allocate all the memory that we need up front and take from that memory what we need for each one of these individual subsystems. So that is what we're going to be setting up now. However, to do that, we are going to need something to sort of handle that allocation for us. And I mentioned early on in the series that the memory layer was only sort of just the start, that it is not by any means finished, and that we are going to be adding things to it. And so that is one of the things we're going to be doing today, is sort of extending this a little bit, as well as fixing some issues that I found over time. So what we're going to create today is we're going to create our first allocator. And with that, we are going to start using that immediately to allocate our application state. And then we are going to use that to allocate the states for all the subsystems. So we're going to create a linear allocator because it is the simplest and makes sense for what we need in terms of application state for now. Linear allocator is not the only one we're going to create, but that's where we're going to start. So, what is a linear allocator? A lot of you probably already know the answer to this, but as you might expect, a linear allocator, first thing it does is allocates a block of memory. We'll say, I don't know, 64 megs or something like that. And so it grabs a huge chunk of memory and holds on to that block. And then anytime you ask the linear allocator, hey, I need 2 kilobytes of memory, for example, the linear allocator then says, okay, I'm going to move my pointer forward within that block of memory, and here is the address for the block of memory that I'm giving you. And then it sort of keeps track of those allocations as time goes. And because it's linear, it means that you start at the very beginning of that block of memory, and you keep allocating or moving the pointer forward every time allocate is called. But it also means that there is no way to free that memory because it does not keep track of that. It only moves a pointer forward. So you can only allocate on it. You cannot actually free on it unless you free everything. And I know that sounds like a little bit of a strange implementation, but the reason for that is because it's the fastest. And there are going to be a lot of times where we're actually going to use a linear allocator because we don't actually need the power to allocate or deallocate sort of randomly. It makes sure that we have no memory fragmentation whatsoever, and we can just simply say, you know what, we need to allocate some memory for this, and it almost immediately gives it back to us with very, very little overhead. And it's going to wind up being much faster than calling malloc every time for sure, as well as obviously references to that will be much faster because we're not going to be fragmented. So I hope all that makes sense. So the first thing we're going to do is actually add our linear allocator, and we're actually going to we're going to set up what I'm going to call a unit test library as well to be able to test our allocator, because there are actually several things within this system that we actually want to run code tests against to make sure that they work the way that we think they work, so that we don't have to go chasing down bugs later on. And I'm not a huge fan of writing unit tests for every little section of code. That's not, I don't think that's productive, but I do think that there is value in that in some cases. So we're actually going to touch on that hopefully a little bit today as well. So let me see, are you going to talk about this in a structured video in the Kohi series, or is this just going to be on this live stream? So this particular thing is just going to be on this live stream. I'm going to probably mention this. I might make a highlight video as part of the Kohi series and then point to this live stream, which will be posted on the channel. But yeah, I'm going to implement this here on the live stream and then reference it from the series. Let's see. What would you do when the block of memory gets filled for that arena of memory? Expand it by 2 or move the whole block? Neither of those things. So that's a good point, though. So with this linear allocator, basically the way it's going to work is you are going to tell it how much memory you need up front, and that is all it's ever going to implement, right? Because I don't want to put all those checks in there to say, hey, you know, we need to expand this if it needs to be bigger. There's a couple reasons for that. First, when you expand it, there's a high chance that you're going to wind up with a completely different address of memory for the main block of memory, which means that any pointer that you've handed out based on that is now going to be wrong. And that's not something that you're going to want to sort of try and rectify. You're not going to want to track that. And there's not really a clean way to do it, right? At least not in a way that requires, or that doesn't require lots of overhead, right? And so the goal of this is going to be to keep it as simple as possible for speed. And what I'll do is I'll probably put something in there to say, you know, if our total allocated amount exceeds what is allocated, I'll probably just throw an assertion. And at that point, the programmer can adjust it, right? So that is the way we're going to handle that. Because realistically, in shipped code, you're not going to have situations where that should really differ all that much. Once the product is locked down, you'll know how much memory you actually need. So it doesn't really need to be dynamic, right? We don't need to ship that. So I hope that makes sense. Okay. So I think what I'm going to do is I'm actually going to create a new folder here. Because I don't really want to put this under core. I think I'm going to do a new folder, and I'm going to call this memory. And I realize K-memory is under core. I might wind up moving that later, but I'm going to put our allocators here into this new memory folder. So the very first thing I'm going to do is create a linear allocator.h. Right. And of course, pragma once. And I'm going to include defines.h. And that should give me all the types I need. We are going to type def a structure. And we'll call it linear allocator. Okay. And in that, we are going to store a couple of things. So we're going to have a U64 for the total size, right? That's going to be the size in bytes. Let me just fix this because that's going to bother me. We are going to have a U64 for allocated. That's the total allocated memory. So every time we call allocate, that'll obviously move forward. And then I'm going to do a void pointer, which is actually going to be our memory itself. That's the block of memory that this is going to hold. And then I'm also going to hold a B8 to say owns memory. And this is going to be how we're going to write all of our allocators with that owns memory. Whoops, got a typo here. I was wondering why those types weren't showing. So this owns memory is basically going to be set based on what we pass to the create method. So we're going to have the ability to pass in this memory from another allocator, right? So at some point, we may have an entire arena of memory that we pull from to actually create this allocator from. And that's going to allow us to potentially avoid some additional calls to malloc if we want to. So I want to build that in from the start and just say if we are the ones that call malloc essentially and allocate the memory, then we own the memory. Otherwise, we do not own the memory, and it should not be freed when this is destroyed. I hope that makes sense. Okay. Questions. So then for situations where assets need to be stored in memory and freed and not used, a different allocator may be used. Yes. Subsystems can be predictable, so linear allocator works here, I guess. Yes, exactly. So this is not the only allocator we're going to be writing. We're probably going to wind up with 5 or 6 different allocators that will each work a different way depending on our needs. So this is just the very first one, just to sort of get our feet wet with it, because it's the simplest to implement. Okay. So we need KAPI because we want this to be exported. We're going to return type void, and we're going to say linear allocator create. And to that, we are going to ask for a total size. So how much space should be allocated by this allocator. Or if you're passing it memory, how much memory are we passing it? So next is void pointer memory. So this is the memory that would be passed from somewhere else. If it's allocated from somewhere else and we don't want to own the memory, we would pass this. Otherwise, we pass 0 here. So if we pass 0 here, then this is the size that is going to be allocated. If we pass an actual allocated block of memory here, then this is how big that block of memory is. Okay, and then we are going to have an out allocator pointer to a linear allocator, right? And that is basically what our linear allocator create is going to look like. So obviously we have a create, so we also need a destroy. So I'm just going to destroy, and in this case we only need a pointer to the allocator. Okay. Let's see, I was always curious about memory allocators. Thinking about it now, a linear one can work if you know well in advance all assets for a game and then just clear it all at once, since once the scene is no longer needed. Yep, exactly. So that's another example of where a linear allocator would be good. You could also use a stack allocator for that. And I'm not going to go into a stack allocator now, but if you think about the name of it, it probably makes sense on how that would work. So we're going to be creating those as well, but that's just a hint of things to come. Anyway, so from this, there are going to be 2 methods that we're going to create. So we have our linear allocate allocate, we're going to call it, which is going to return a void pointer. So this is what's actually going to return to us a block of memory. So we'll call this linear allocator allocate. And this is going to take a pointer to an allocator, right? So what allocator we're allocating from, and then the size that we want to allocate from, right? And so that will just return our pointer there. And then we're also going to have, we're going to have a void return type function, and we're just going to call this free all. And this is going to basically free everything in the past allocator, right? Which in our case is basically going to essentially reset our allocated to 0, effectively putting our pointer to the beginning of this memory, okay? And that is the only way we can actually free from this allocator is through this, right? We can't do individual frees. So this is the entire interface for our linear allocator, okay? So I'm just going to copy these guys. I'm going to go to here, create a new file, linear allocator.c. We're going to include linear allocator.h, And I'm just going to turn these, turn these into functions real quick. Whoops. Okay. Great. So now that we have all of these, we're just going to fill these out. And again, this is not going to be too complicated. It's going to be, should be pretty relatively straightforward. So first thing we're going to do is check to see if we actually have an out allocator pointer, right? Because if this is past 0, we don't want to do anything. Okay. And then the next thing we'll do is we'll go ahead and set the total size to total size, right? Because either way, whether or not we own the memory, that total size is going to be true. Okay. We are going to set the allocated to 0. We are going to set owns memory, not pwns memory, owns memory, equal to, and we're basically going to say if memory equals 0. Okay, and so if memory is equal to 0, that means we own the memory. If it's not equal to 0, then we don't own the memory. Okay, and then we are going to treat this differently depending on how memory, or what is passed in memory. So if memory is passed, then all we're going to do is say out allocator memory equals memory. Okay, and that's it. Otherwise, we will need to allocate some memory. So this means that we need core k memory. Okay, and now we will say out allocator memory equals k allocate, and we're going to want total size, and we're going to want a memory tag. We're actually going to want to probably set up a new memory tag for this. Yeah, I'm going to set up a new memory tag for this. So let me go here, and I'm going to set up a new memory tag for each one of our allocators. So I think right after this, I'm going to say memory tag, call it linear allocator. Yeah, that should work. Right, so every time we add one of these, we'll go ahead and we'll add a new tag for it. That way we can track it a little bit easier. Which means right here, we need to shorten this. I'll just call it that for now, so that we have our string mapping set up still. Okay, and now I can use this guy here. Okay, and so there our allocation is done if and when we need it. Okay, and that is all there is to creation. The destroy is going to be pretty similar, so I'm actually just going to copy this real quick, and instead of out allocator, these are just going to be allocator, right? And then total size, we're just going to actually zero all this stuff out, and then we will go ahead and check, probably move this here. Okay, so if the allocator owns the memory and the memory actually exists, then we're going to actually switch these two around. So allocator memory, we will call k free for that. Pass allocator memory. Actually, before we can set this, move that down here because we need the total size for this. And the memory tag here. Get rid of this line. Boom. Okay. And otherwise, we can just set this to 0. So if we don't own the memory, we're just going to set that to 0, right? Because it should be the responsibility of whatever passed us that memory, the owner of the memory, to clear it out at that point. So, okay. I'll go ahead and set also allocator owns memory to false. And that should pretty much cover us, right? So that is our destroy. Let me take a second here to just read through. All right. Oh, hey, Wensheng. Welcome to the stream. Appreciate you showing up. Marcus, hey there. What are you working on? We are working on allocators right now. So we're working on a linear allocator just to be able to use for our application state. So we're building out that linear allocator now. We're probably about a little less than halfway done. And then we will jump back to that. So that's what we're doing right now. And Coderoid, hi. How's it going, man? Welcome to the stream. All right. So the next thing that we need to do is check our allocation, right? Or fill out our allocate method, rather. So the first thing we're going to want to do is obviously check to see if we have an allocator. And then we want to check to see if there's memory, right? Because that's kind of important. All right, and now what we're going to do is we're going to check for the overflow. And this is really going to be the only check that this allocator actually does. So we're going to say if allocator allocated plus size is greater than allocator total size, right? So in other words, if we hit this, then that means that there's not enough room left in this allocator to actually do anything. And so what we're going to do is we are going to calculate the amount that's actually remaining, and we're going to report an error, and we're going to return a null pointer here. So we want to say u64 remaining equals allocator total size minus allocator allocated, right? And that'll give us the remaining. And then since we're going to report an error, I need the logger. So we'll include that. Core logger.h. And we will say, should I do fatal? No, I think I'm going to do error for now. I might come back and change this to a fatal error. I think for now I'm just going to leave it as an error. So I'll say linear allocator allocate tried to allocate. I'll put LLU, that's the token for a 64-bit unsigned integer. So we'll try to allocate that many bytes only, and then LLU be remaining, right? So this is going to just take size and remaining. So in other words, it's going to say we tried to allocate this many bytes, we only have this much left, okay? And then we're going to return 0, right? Which is the way that malloc sort of works too. So if 0 is returned from this, that means the allocation failed. Okay. So the next thing that we need to do is we actually need to get our block of memory to return. So in order to do that, we're going to have a void pointer that we're going to call block, and we are going to set that to allocator memory plus allocator allocated. And that is basically going to take this pointer and move it forward by this many bytes, okay? And that is going to give us our block of memory that we are going to return. So obviously our first allocation, this is going to be 0, right? So it's basically going to return this pointer. If we're 2 kilobytes in, then this will say basically be 2 kilobytes. It'll be this address plus 2 kilobytes, and that'll give us our actual block here, right? So just some quick pointer arithmetic there, and then we will say allocator allocated plus equals size, just so that the next time this will work, and then we will turn block. Okay. Now, if we actually happen to call this and there's no allocator, or potentially there's no memory for some reason, then we actually need to report that as well. So we'll go ahead and say k-error, and we'll once again copy this function name, and we'll say provided allocator not initialized. Right, and again, we'll return 0 to signify that that operation has failed. Okay, and that is all there is to creating a linear allocator, right? It's really simple. And the free all is actually even more simple than that. So I actually need this same check here, so I'm just going to copy pasta that. And then inside here, we're going to say allocator allocated equals 0, right? So literally all we're doing is we're just moving that pointer back to the beginning. And then as a sort of safeguard, if you will, I'm actually going to go ahead and zero out the memory, just because it makes it a little bit easier to see if we're debugging memory used by this when it's actually been cleared, right? So I'm going to pass allocator memory and then allocator total size. Okay, and that just will blank that out for us. Okay, and that is our linear allocator. Nice and simple, right? So doesn't look like there's any questions on that, so I think the next thing I'm going to do is we will see, how are we doing on time? I think I'm going to go ahead and set up a small testing project in here so that we can start testing our code, because I think that that is an important thing, and this is going to be crucial to a lot of our application. So I think it is worthwhile to maybe do some tests on that. So let me see. Probably this line, void block equals, it says expression must be a pointer to a complete object type. Are you, let me build this real quick and see if I get the same thing. Nope. One thing you could try doing, I'm going to guess you're probably using Visual Studio, aren't you? Like full-blown Visual Studio? Take a sip of my Kohi. Yeah, okay. So it's probably a little bit stricter about this. So one thing you could probably do is just cast this to a U8 pointer. Right? You might have to do something like that. I'm not 100% sure. Try that and see if that works for you. Gets rid of the error. Okay, all right. Yeah, so sometimes it wants a little bit more specificity on the type that you're actually doing, so that way it properly performs the pointer arithmetic. So the smallest unit that we can use, obviously, is a U8, so that's the reason I chose that, right? Because technically a void pointer is a little bit larger than that. This could be any size technically, right? So yeah, Raz, that's half true. It's a little bit weird as far as how they implemented that. It enforces it in some places and not others. It's really kind of strange. So but yeah, to be safe, you could just do this, and that will make it operate the way that you need. Okay, so tests. So I think the way that we're going to do this is I'm going to create a new folder that is next to engine, right? So we have engine and testbed here. So this is actually in the base directory. So I'm going to create a new folder, and I'm going to call this tests, right? And this is going to house a third project that we're going to write all of our test code in. And this might seem a little bit pointless, but I've actually found a lot of bugs and stuff by writing these tests. So I find in some cases, especially with stuff like this, that it helps a lot. So so in that tests, we are going to, I guess we'll start off by creating a main.c. Actually, we need a source folder first. And then in that, we will create a main.c. Okay. And then let's go ahead and also create a build.bat. Right, just for those of you who are still sort of using that system. And I'm actually, this is something that I figured out ahead of time, so I'm actually just going to paste this in. And this will be available on the repo when I'm done. But this is basically the compilation for the test, right? So it's basically just going to output a tests exe. And this is just going to be a separate executable that we're going to run against our engine code, okay? And for those of you guys that are on a different platform, such as Linux, I'm going to create a test.sh, build.sh rather. Oops, that should be in the root directory. Yes, okay. And this basically just does the same thing just for the correct platform. Okay, so there's that. We'll hook that up in a minute. And then one of the first things I think I want to create is actually an expect library, right? Something that basically says, okay, well, here is one value, here is an expected value, compare them and see if they're the same, and if not, log an error, right? Tests are where the tests are, and testbed is where they go to sleep. Yes, exactly. Yeah, testbed is probably not a great probably not a great name, but it is sort of our testbed application, so that's what I'm sticking with for now. Anyway, I'm going to, next to this source, I'm going to create a new file, and I'm going to call this expect.h. And this is going to give us some utility methods that we're going to want to use throughout our tests, right? And so the first thing I'm going to want to do is include, and we're going to say core logger, right? Because we're going to need the logger. And note that I'm using these guys instead of quotes, because now we are including something that is external to this particular project, right? And so we need that, and then we also need include what was it, math, math, because we're going to need that for some comparison functions, okay? And this bit I've actually already kind of written ahead of time, so I'm just going to sort of paste this in and explain how all this works one at a time, because this is something that I've actually written in a few different libraries, so I didn't feel the need to rewrite it. So the first thing we have is a macro called expect should be, where we pass something that's expected and something that's the actual, right? And it basically just compares these to say, well, if they're not the same, then we throw a k error. But the powerful part of this is, and the reason I did it as a macro, is because it says, hey, we expected this, but got this, right? Here is the file and the line number, right? And then we actually use the file and line macros. And so what this does is it actually outputs the file path colon line number, which then makes that clickable in this console down here. which is really super helpful when you're actually running these and you have a failure. You can very easily navigate to it. Okay, so that's the first one. That basically just compares two numbers to make sure that they're the same. However, we also need one basically for the opposite of that. So expect should not be, which basically checks them to say, hey, if they're equal, then we're going to throw an error regarding that. Okay. The next one is going to be for floats specifically, because floats require a little bit of a tolerance when doing equality checks, right? So we are basically going to use this as our tolerance for right now. We may wind up using kfloat epsilon eventually, but because of rounding errors, floats are never exactly the same. So basically what we do is we take the absolute value of the expected minus the actual, and then say if that's anything over this, then we say, hey, these are not considered to be the same. Okay, and then as you may have guessed, we also need one for Booleans. So expect to be true is basically saying if actual passed in is not equal to true, then we throw an error to that effect. And then we also need one that is expect to be false, right? And this is, we'll probably add on to this as we develop some more tests, but for now, these are the main functions that we're going to need for our testing library, right? Okay. Next, I wasn't actually going to write this right away, but I think I'm going to go ahead and step through it, is something called a test manager. And this is basically a way for us to be able to quickly register tests with a manager object that essentially will run them all for us and report and keep counts on how many failed, how many succeeded, so that all we have to do is write the actual test and we don't have to have all this boilerplate code every single time we add a new test. So I'm actually going to go ahead and just block that out now. And again, this is actually a bit I've written ahead of time, just for expediency purposes. So this might be too granular, but how are file and line known? Those are macros that are defined by the compiler. So at compile time, it basically replaces those tokens with the file path and the line number respectively, like inline, as part of the preprocessor. Hope that makes sense. Okay, so I'm going to do test manager.h, and this one I'm just going to go ahead and paste in. Okay, and what we're looking at here is we obviously use our define so that we have our types, and I'll come back to this. The first thing that we define here is a pointer function for a test method, okay? And this basically takes no parameters, right, but returns a U8 type. Now, the reason I'm doing this is because I don't want to return true or false. There is a third possibility. So you have false, which is 0. You have true, which is false. 0 means the test failed. True, which is 1, means the test was successful. And then we have this bypass 2 up here. And that means that the test is being bypassed. And that is so that we actually get special logging for a bypassed test, which basically says if there's a test that we've written, but maybe we don't have the code behind it, or maybe that test is currently broken, but we don't want that to hold us up, we can bypass the actual test. And I'll show you guys how to do that when we actually start scaffolding tests. But if we have a bypass test, it returns 2, and then the test manager is smart enough to know, hey, this test is bypassed, so we don't need to worry about it, but log it just in case. Okay. AKA compiler magic. Yes, exactly, Raz. Aside from games, will there be a time where I'll be writing physics simulations using Kohi? Aside from games. Not 100% sure what you mean by that. If you could clarify that a little bit, I'd be happy to answer it. Okay, so let's go ahead and create our test manager C. Let's see. And again, this is something that I've sort of written before, so I'm going to go ahead and just paste this in. All right. So there's a lot going on here, so I'm just going to run through it real quick. So here we are using a DArray, which is dynamic allocation, but since this is a test library, that's okay. We're not as worried about performance, at least from the test manager standpoint. So what this does is it holds an array of tests, right? And here we have that static array being held. Again, this is an example of static state. It's on the stack here. I'm going to avoid doing this in the future in the engine, but again, for tests, it doesn't really matter. So each test entry has a function pointer in it to the actual method that'll be called, the test method itself, that will actually return the code, and then a character pointer description of that particular test. And so the way this works is we basically just add test entries by registering them. So we have this register test here where we pass our function pointer and then a description. And we go ahead and create a test entry based off of that and push it to our tests array that's here, right? And then when we actually call this run tests, it goes through every test that is registered and runs it. And so the way that this works is we have a counter for passed, failed, and skipped. That skipped is the bypass that I was talking about earlier. And here we have a count, which is the total number of tests that I've run, the total time for all of the tests to run, and then we have a time for each individual test, right? And so the very first thing that we do for each one of our tests is we say we get a clock started for that test. We run the test by calling the function pointer to it, store off the result, and then immediately stop the clock, right? So this between here and here tells us how long the test took to execute. This can be used for performance profiling later on if you wanted to. And so we have that. So here, if the result is equal to true, which if you recall is equal to 1, then we increment the passed. If it's equal to our bypass, which is 2, then we throw a warning saying, hey, this particular test was skipped, right? And so we just output the description of that and increase the skipped count. And then if it failed, we throw an error, so we get nice red text. And then say, hey, this particular test failed, and increase the failed status, okay? Next, what we do is we output how many tests failed for each, as we're going. So if we have a failed test, then we say, okay, X number of tests have failed so far. Otherwise, we just keep putting success. So we keep putting success until we actually run into a failure, and then we output the number of failures as we're running from then on. Okay, and then as this runs, the clock updates after each individual test for the total time. Okay, and then right here, I'm sorry, not the total time, but the yes, the total time. Okay, so and then here we say we executed the test number of however many, how many were skipped, and then here we say how many seconds that test took, and then how many seconds overall we're running currently, okay? And this is just a string format that puts out all that information for us. Finally, we stop the clock, and then we say, here's our results. This many passed, this many failed, this many skipped, and then there we are. And actually, I probably could add like a total time. Technically, it's going to wind up being the same as this. But yeah, there you have it. So I hope that makes sense. Okay, so let me just catch up on the chat here. Does that also imply these test functions are run by the compiler and not executed manually by developers? So I think what you're asking is, do we have to execute this manually? So yeah, you do have to run the executable. We are eventually going to set up our build process to sort of do this every single time, at least as part of our continuous integration that we'll eventually set up once we get further along in the project. We're going to set something up that actually runs that for us, but for now, no. You have to run it manually. Are you going to push this through GitHub? Yes. Yes, all of this will be pushed to the GitHub repo once we're done. Okay. All right, so that is the test manager. So now we can start filling out main.c. Thankfully, main.c is actually pretty straightforward. So the way that I'm going to do this is actually I'm going to include test manager h, and then I've already got part of this written, scaffolded as well, just for expediency. So I'm going to include the logger, and then I'm going to basically put something out that says test manager init, which is going to set that up, say that we're starting the tests, execute the tests, and return 0. Okay. Now, what needs to happen before we actually execute the tests, right here, is we actually need to register our tests here, right? So this is what is going to call some registration functions that we're going to set up that then turn around and register all the tests for that particular unit. Okay, so under source, we're going to create a new folder called memory. And we're going to basically mirror the folder structure of what is under engine, right? So this is going to be a memory test. So we are going to say under memory, create a new file, linear allocator tests.h, right? And the only thing that the h is actually going to have in it is just a quick pragma once and then a register tests. Because all the implementation will actually be in the C file. So what we'll wind up doing is we're going to take this linear allocator register tests and go back to main, and we will include memory linear allocator tests.h, right? Make sure you include the tests, not the actual linear allocator. And then we'll just call, oops, this here. And this is how we're going to register our tests, right? And so this function will actually be responsible for registering the tests that we're going to put in the C file here. Okay, so I'm going to create a new file and call that linear allocator tests.c. We will include linear allocator tests.h and also memory linear allocator, since that's what we're going to be testing. Okay, and then obviously we need to define this guy. So we're going to go all the way to the bottom here. Oops, keep doing that. Okay, and this is where we're actually going to perform the registration. So one more include we're going to need here is the what is it? Test manager, I thought it was. Yeah, test manager. .h. Okay. I actually might need to go up a level here. There we go. Okay, so now we have our test manager so that we can call our registration function. And now we actually write our tests. So the first thing that we're going to do is we're going to write a test basically to test that the create and destroy works properly. Which actually I probably ought to include defines also. So I'm going to call this U8 linear allocator should create and destroy. Okay. And this one is basically going to be a linear allocator alloc, and then we call linear allocator create. We pass the size of U64, which is basically saying this is how large we want this allocator to actually create. It's how much memory we want to allocate, rather. And I'm going to pass 0 for the memory because we want this allocator to own the memory in this case. And then a pointer to the allocator, which is just going to be the address of alloc. Okay. And then here is where we use our expect. So we actually need to also include expect, right? And we'll say expect. First thing that we want to do is say expect should not be. The expected value should be 0, and the alloc.memory should be compared, right? So this is the actual, and this is what's expected, or in this case, not expected, right? So this is basically saying alloc memory should not be 0, okay? And then we want to do expect should be, and we will say size of U64, and we will pass alloc total size, right? Because that should have been updated by this function. And then we also should expect should be 0 alloc allocated, right? Because it should start off with a brand new allocator. Nothing should be allocated, right? So we need to verify that. Let's see. Let me just read some comments here. David, is that you? David? Who's David? Hi, how about Arch Linux? What about Arch Linux? Are you saying is it supported? Or I'm not sure what you're asking there. Technically, as long as you have all the required things installed, like a compiler and the Vulkan SDK and all that, yeah, it should work. That's quite a long function name. Yes, it is. David? Yes, okay. Oh, right, yeah. So it should be supported. Yeah, it should work on Arch. I haven't tried it on Arch. My Arch install is actually broken at the moment, but it does work on Ubuntu for me. So, but yeah, I don't see any reason why it shouldn't run on Arch. Okay. All right, I'm gonna move on. Okay, so now that we have that, we should also check the destroy. So we'll say linear allocator destroy. We'll pass the address of allocator, right? And then we are basically going to want to test. We're going to want to test the memory total size and allocated, but now they should all be 0, right? So I'm actually just going to copy pasta this, change this to should be, change this to 0, right? And that will mean that the destroy has worked properly. And then if we get down here, we should just be able to return true, okay? And now, in order to register the test, what we do is we call our test manager register test, right? And we pass it the function, right? So here's the test function. And then a description of that. So linear allocator should create and destroy. Okay. And there we go. So that is how the registration works. So I tried to keep it as lightweight on the test side of it as possible. So that way when we go to actually utilize this, there's not a ton of overhead to actually make this work. Okay. All right. So for right now, I want to actually test this, but there's a couple things I have to do within the environment here to actually get it to build and run. So for those of you that are using the old school build system, this will work. For those of you who have switched over to the new makefile system, we are going to need a couple of new files. So I'm going to create a new file called makefile.tests.windows.make. All right. And this is another one where I really do not feel like explaining this at length, so I've gone ahead and made this ahead of time. It's almost exactly the same as testbed, actually. So it builds an executable file, and whoops, I've actually pasted the wrong one in here. It builds an executable file just called tests.exe. That's really the only difference, right? And then we need a new file, makefile.tests.exe. Linux dot make. Okay, and the Linux one is very similar. Does the same thing just for Linux. Okay, so now that we have those, now we should be able to come up here to our tasks, and we actually need to create a couple of tasks for it. So I'm going to go ahead and paste this in as well, because it's basically a copy of, well, really the test bed. So let's see. In fact, I'm just going to copy. I'm going to copy test bed here. Just do it this way. Right. So build tests. We'll say build unit tests. This is going to be changed to tests. Right. Okay, and options, we're going to run this in the tests folder, and then everything else should be good to go. So that's build unit tests. And then our build everything, we're actually going to add this to that as well. So let's see, our build all dot bat, we are going to take this guy and change this to tests, and that's all we should need for that. Our build all sh, we're actually just going to copy this and change this to tests, and that's all we should need for that. Go ahead and do the Mac OS one as well, which this one looks like it's kind of outdated, so I'm not sure if this one's actually going to work. I don't have a platform to actually test this on, but any of you guys out there that are running Mac, feel free to let me know if this doesn't work, and I will fix it. Okay, so last, we also need to clean all, so I'm just going to copy this, tests, that, I believe, should be everything we need to build it. So that is our build. Right, okay. Next, we need launch. So here we have our testbed exe for Windows and Linux and Mac. So technically speaking, we are actually going to need, I guess, duplicates of these. So I'm just going to copy all three of these, quite frankly, and just change the properties needed. So I'm going to say unit tests, and I'm just going to copy pasta this here, and just change this to tests. That should be fine. Tests. I think that's the only change I actually need to make. I think everything else should work as is. Okay, so let's go ahead and build. It looks like it built linear allocator fine, but what is it saying we have? Oh, you know what? I probably didn't include clock. Linear allocator tests, or is that test manager? That's test manager. I included clock and logger. Are those functions not exported? Oh, they are not. Okay. Something I would not have found had I not written the unit tests. So this needs to be exported. So we'll just slam a K API in front of those. Build. All right. Got a couple other things going on here. Implicit declaration. Oh. I thought I included K-string. String format. Doesn't that have... Ah, it's because I haven't written it yet. Okay. So that's fun. All right, so we need to expand our string library because this requires something that I have not yet written in the Kohi series. So let's go ahead and get that in now. So basically the string format works a little bit like what you might expect from C# if you've ever used that, where you basically pass in a format string and then it does a bunch of string formatting and returns a new string under the hood. And that's actually what we need to create, right? So this one I actually have written already. So I'm going to copy this and paste it right in here. So basically we have a destination buffer that we write out to. This should be big enough to actually contain the entire string that we need. And then our format string, and then all of our individual parameters that we pass in here. So we have that, and then we also have one that's available for variadic arguments. Yeah, we need one of each of these, right? So let me go ahead and slam in the definition of this, and then I will explain it. So what we need is in the C file, we need two functions. So we need our string format, which basically says if the destination buffer exists, then we use the built-in VA list type. I have to use this type because I've had issues with just using VA list. For some reason, IntelliSense bleats about it, but if I use this built-in version of it, it works fine. So if this doesn't work for you on Visual Studio, you might have to just do that. So just heads up on that. Anyway, so this is the arg pointer list, which basically takes this and based on the last fixed argument, takes all of these and builds a list out of it internally. And then we can then pass to string format v here that list of arguments. And I'll come back to that in a second. And then this VA end essentially just cleans up the list that was built here and returns the number or the size written. Okay? So what we do here is, and this is kind of a little bit of a hack, it's kind of big for a buffer, but it does fit on the stack. So we create a huge buffer, and then we call VSN printf, which takes a variadic list of arguments, and we pass buffer our size here, and then the format string. It's nulls out the very first character of after the number of characters written. So when this returns, it says how many characters were written, and then this basically goes after that and null terminates the string. And then it performs a copy to the out buffer from the internal buffer here. Since this is stored on the stack, this will obviously go away when we exit this scope here. So this copies out to the destination and then returns the number of bytes written. If, for some reason, the destination does not exist, it returns a -1. Okay? Hope that makes sense. Okay, one last thing. These are both exported, so we should actually be able to build successfully now, I believe. No, it looks like I'm still seeing some errors in here. Oh, that's probably because we did not include stdarg. So this VA start and VA end and VA list, all that, actually requires us to use stdarg.h. Okay. Still have some warning in here. What is this? Implicitly declaring library function VSN printf. Thought I included string h. Is that not? I thought that was included in string h. I can't remember now. Let me ask the good old Google machine. see. Oh, it's stdio. Okay. Sometimes I just can't remember all of it, folks. All right. Now we built successfully. So if we go into our debug tab here, we change our launch to our launch unit tests and run. That is in an external window because I don't think I actually switched that over. So it came up and immediately disappeared. Let me change that. Instead of new external window, I'm going to change back to integrated terminal here. For that one and here. Okay. All right. So here is some output. It's not what we expected, but that's fine. It kind of gives you guys an idea of how this library works. So here, we see here that we started our tests. We expected 0, but got a rubbish value. So we'll have to look and see what is going on with that. But this is the nice part here, is when it fails, it gives you the actual file and the line number, which in VS Code is actually clickable. So if you hold Control and click that, it'll take you straight to it. And this is saying this is where it failed. So this is basically, it's saying that it expected the memory to be 0, which means something in here failed in the destroy. So I'm actually going to debug this real quick. Put a breakpoint here. And these all pass, right? So I'm going to step into allocator destroy. And let's see, allocator allocated is 0. Oh, you know what? We didn't zero out the memory. I think that's the problem. Yes. Yeah, because this still has an address in memory. That's why. Okay. So this, folks, is a classic reason why you should write unit tests for things like this that are actually testable units of code, is because you can catch stuff like this that you miss along the way. So technically speaking, this should happen whether or not we own the memory. We should always zero it out, right? So if we own the memory, we need to free it, but if we don't own it, or if we do own it, we should always be setting that to 0. So I'm going to go ahead and build that and then run again. And I'm just going to turn off my breakpoint. And now we see here we executed 1 of 1. And it actually did it so fast that it's not even picking up the time, which is interesting. Okay, so we have 1 passed, 0 failed, 0 skipped. Okay, so with all that, we will write just a couple more tests. And then we'll jump back to actually implementing this in code. So I actually want to just test allocation real quick. So I'm just going to, I want to do a test for allocating all of the space, allocating a multiple allocations for all of the space available. I want to try over allocating and make sure that it actually throws an error like it's supposed to. And then I want to try allocating all the space and then freeing it. And that should really cover us. So I have actually written these ahead of time as well, because I know it's going to take a while to actually step through this and write them all. So I've actually written a few more here. So what we have here is we have, first off, a multi-allocation that takes up all the available space in the allocator, right? So we have the max number of allocations we can do here is 1024. We create our allocator with the size of U64 with that many allocations. We loop through and call allocate that many times, right? So however many allocations we set up here, we call it that many times, allocating that many times. And it should fill the entire buffer, right? But it shouldn't overflow, okay? And then we could do some additional checks down here to see what the allocated amount is. I'm probably just going to put breakpoint here for now and test it. And then we go ahead and destroy it to clean up that memory, okay? So we do that. We do an over allocation here. So we say our max allocations is 3. So we loop through that to fill up the buffer. And then we throw a message out there saying, hey, the following error is intentionally caused by this test. And then we try to ask for another allocation. And here we should expect that that should return 0 and that the allocated should not have changed. And if that is all as we expect, then we're good to go. I will put a breakpoint there as well. And then we have allocation for all space and then free. So we're just testing our free all method here. So I'll go ahead and put a breakpoint there. And then I'm going to go ahead and paste in the test registration here as well, so that we don't burn a whole bunch of time on this. Looks like I actually missed one. So yes, I did miss one. So let me go here. So we have our linear allocation where we allocate all the space, right? And this is all the space via a single allocation. This is all the space by a multi-allocation, okay? And so we're going to just run these real quick and see what we get. They should all pass. Okay, so we have our breakpoint here. So looks like we didn't run into any errors here. If we look at the allocated, it's 8192, which is what we expect, I believe. Yeah, because the size of this is going to be 8. 8 times that is 8192. So that is actually what we expect. So I'll go ahead and move on to the next one. So this one, we get our notice saying we're intentionally causing an error, and here is that error. So we successfully tried to allocate 8 more bytes. Only 24 bytes remaining though. That's kind of strange. Let me see. So allocated is 24. I'm wondering if I'm just outputting the incorrect value there. Remaining is total size. You know what? Let me go back and put a breakpoint there because that does not seem right to me. So I'm going to restart this and step into that. Whoops. I need a breakpoint there. Okay. So here the allocated is 24. The total size is 24. So technically our remaining is nothing. Oh, I see what I did. See? Unit tests save the day again. I have an equals there, and it should be a minus. This is why they're important. Okay. So now that should say only 0 bytes remaining. Okay, so that's actually what we expect. So our block should be 0, and our allocated should be the size that we expect, which it is, so that passes. Okay? And then our final test here is multi-allocation and then free, and we see here that that has been properly done as well. So we know at this point that our tests have all passed, so we know our allocator is good. Had we not written this, we would have had to trace down some of those bugs that were in the code. So I probably won't be writing a lot of these tests on stream or in the series going forward. I'll probably just silently add them after this, but I hope that this helps you guys understand the value behind this. All right, are there any questions before I move on? I will take that as a no. So I'm just going to switch this back to Windows Launch. And at this point, I am going to start implementing this at our application layer. Okay. Do you know of any resources about writing unit tests, like do's and don'ts? Not any offhand specifically. I would say probably just read up on it a little bit, to be honest. One thing, a couple of things that I can point out is that you never want to be using different sets of data every time you execute a test. For example, if you're testing something having to do with date times, you do not want to use the current date time for that test because it will change every single time you write the test. You want to use a set of data, or a predetermined hard-coded set of data to test against. That way, you don't get intermittent failures in your unit test, and you know exactly what data you're testing every single time. So there's that. There's also, try not to put too many things in one test. Try to keep your tests as focused as possible. And I would say, there are certain things that you probably don't need to unit test. You don't need to unit test that the creation of every single thing is successful. I did it in this case because of the memory allocation, but you don't always necessarily need to do that. So that's another thing. And not everything will be unit testable. So there are going to be code. There's going to be lots of code out there, particularly on the GPU side, that may not be unit testable, or at least not easily unit testable. You may have integration tests that you have to use instead, and that's a completely different thing, which we probably will be touching on later in the series, but not just yet. But yeah, I would say probably Google for some articles on it, because there's do's and don'ts out there, probably better than what I could tell you. But those are at least some of the ones that I can think of off the top of my head. Hope that helps. Okay. So, how are we doing on time? All right, we're almost at 2 hours. So I'm going to go ahead and put this linear allocator in and start adjusting the state so that you guys can sort of see how this is going to work. I may not get all of it converted over, but I'll convert at least a couple of the subsystems over to use the new way of allocating data, state rather, and then anything else I'll probably cover later on in the series, or silently add it to the repository and briefly touch on it in the series. So without further ado, let's go back to the application, and we are going to modify our application state a bit. So right now we are actually storing this on the stack, which is not great. Sucks, frankly. So one thing that we have is we have this game instance here, and the game instance is basically a pointer to the game state, so it holds the game state, and the engine itself doesn't really know about that, but there are a few things it does know about, right? So this is the game specific state that it has on here, right? And it has a few function pointers and some application config. We're going to add one more thing to this, which is going to be a void pointer to application state, right? And we are going to store the application state on the game side, because it sort of makes sense to sort of allocate all of this at once, right? So this is going to be the application state, and we're storing it as a void pointer because we don't want the game to be able to sort of access, know, or care about the application state. There's no reason it should have to know about that, but eventually when we go to allocate or set this up, this game allocation happens on the game side. So this will mean that the executable is what is actually going to be where the memory is going to be allocated, which means when we go to implement hot reloading, we don't have to worry about memory that's allocated inside the actual engine. So we're going to be making some changes to sort of switch over to that, so that the only time we actually do allocations eventually will be sort of when we start up the executable. We'll call the allocation functions from that, and then that will own the memory, and that way we can sort of swap out the DLL underneath of it and not have to worry about the memory sort of becoming corrupted in the process. So all right, so that's the application state that we've added there, and I think that is probably the only thing that I need to add here. So what we'll do is I will go back here to our application create, and I'm actually going to go ahead and let's see, where was it? Let me just make sure I'm doing things in the right order here. Okay, so here at the top we have this this initialized, right? And initialized sort of tells us whether or not our game state is sort of, or our application state exists, right? And we're doing that because we don't know at this point whether the stuff has been set here or not, right? And so I actually want to get rid of this. And so I'm actually going to do that now, and I'm going to change this initialized to say we're going to look at the game instance, and we are going to say application state. So if the application state already exists, then we know that this was called more than once, and that's rubbish. We don't want to do that, so we want to boot out. If it does not exist, then the first thing that we're going to do is obviously save off the application game state instance here. So we're going to keep a copy of that, but we're also going to say that the game instance application state is equal to allocate, and this is one of the very few allocations that we're actually going to do at this level, right? And this will make sense later on. Eventually, this will wind up being moved too, but we're basically going to stand up the state at this point, so it's okay to do a dynamic allocation here. So we're going to say size of application states, and let's see, we want memory tag application is what we're going to use. Okay, so we will take that, and then what we're going to do is we're going to take this app state that's here, and we're going to change this to be a pointer to the application state. So that way we're not storing the whole thing on the stack, we're just storing a pointer for easy access. And the pointer will be static, but all you're storing at this point is a pointer. So that way we don't have to pass a pointer around through all these functions. We can just look at app state and get it that way. So obviously that means we'll have to change this to a pointer, and we will change the order of that, and so we'll set app state equals game state application state, right? So this is a little bit weird because it's stored in more than one place, but we're doing this for ease of access, right? So this is really just sort of a convenience for us, so we don't have to pass that stuff all around. Okay. All right. So the next thing that we're going to do is we're going to actually set up our linear allocator. So I'll need to include that. I'll put it here. Include memory linear allocator. And right after this, before we initialize anything, we're going to set up our linear allocator, right? So we're going to say we probably ought to actually store this in the game state. So linear allocator, and we'll call this systems allocator. Right, so we'll store that in the state. And the first thing we'll do is we'll determine a size for it, right? So we'll need a U64, and we'll say systems allocator total size, and we'll say that's equal to, for now we'll just do 64 times 1024 times 1024, which is 64 megabytes, which is kind of huge, but it should give us more than enough memory to deal with for quite some time. Let's see. Let me just read some of this here. Shouldn't the first if an application create be an assert, since the function being called twice would be a programmer error? We could do it that way. We're returning false and writing to the console. It's really going to accomplish the same thing, because if this fails, the call to run will never happen. Okay, so yeah, I mean, to answer your question, yes, we could make it an assert, but I don't think it's really going to buy us anything, other than maybe it'll throw a breakpoint or something. But if I recall correctly, oh yeah, this is actually exported, so I guess technically the way to prevent that would be to not export this and just make sure that whatever calls it is internal to the engine only, and just make sure that it can't be called more than once. That way you don't actually run into it. But even if we do, this will still catch it. So I'm okay with that for now. Okay, where was I? So we need to create the linear allocator. So now we have our size that we want to allocate for the linear allocator. So now we need to say linear allocator allocate. And we are going to pass the address of application state rather. And we'll say systems allocator, right? So we'll pass the allocator and then systems allocator total size, okay? And that is how we stand up the allocator that we're going to use here, okay? Nice and straightforward, I think. All right, the other thing I want to do is there's a couple of places where we're sort of setting some application state stuff here, and I want to kind of move all this kind of together up here. So I think the way that I'm going to set this is, let me check, that is running, that probably should be moved. So this probably should be down here. As soon as this is called, that should flip over. So I'll come back to this and fix those errors in a minute. This should be false to begin with. I'm going to take these and move them up here. And then obviously this is a pointer, so that's got to be changed. All right. And then, yeah, that'll work for now. So the first thing that we have here system-wise is we actually have logging, and then we have input, and so we actually want to change the way that these work. Okay, so if we go to initialize logging, we have basically this doesn't really do much of anything, right? It just kind of returns true. We don't have any state here, and this is actually something else that I've wanted to sort of address. But I might actually do that. I'll come back to that. I think for now, what I'm going to do is just create a state object for us to actually be able to use, and then we'll fill it out later. Because we actually need to create this log file, because it's going to make things a little easier to diagnose at this point. So let's see, do I have... But that requires sort of file system access, which we don't have yet, which we're going to need very soon. So I'll come back to this one. So for right now, what I'm going to do is I'm going to create a dummy state for this, because we are actually going to need a state for this. We don't have one yet, but we are going to need one. So this may not be the best example to start with, but I'm going to start here anyway since it's the first one. So I'm going to type def struct. And note that I'm doing this in the C file, because I want the state for this to be private, right? So I'm going to call this logger system state, right? And for now, I'm just going to put in here, I guess I could put a B8 initialized, right? So this will just tell us whether or not it's been initialized, which eventually we are going to need. Right now it doesn't really do anything, but that's fine. So in initialize logging, the way we're going to change the initialize calls to all of our subsystems is we're going to sort of follow the Vulkan pattern a little bit here. And we're going to call our initialize functions twice. And we're going to call it once to say, hey, how much memory do you need to hold your state? And then we're going to pass a null to the actual state. And then we'll call it again after we've allocated memory for that state to actually supply it with the state and actually perform the initialization. So what do I mean by that? First thing, we're going to take a pointer to a U64, and we're going to say memory requirement, right? And this is going to basically report to us how much memory is required to perform this initialization routine. And then we're going to take a void pointer called memory. And actually, I'm going to call this state. And this is going to be a block of memory that we're then going to hold the state in. Okay? And we're going to keep a copy of this, similar to how we did at the application level, which we're going to say is a pointer to a system state. And we'll say state, if I can type, pointer, right? And that's going to be static. So again, we do have a static pointer here, but that's the only thing that's kept on the stack, right? And so what we'll do here is we'll say if state equals 0, then we're going to just simply return. And before that, we are going to dereference memory requirement, right? We're going to set that equal to the size of logger system state. Okay, so the way that this is going to work is we report the size no matter what, right? So we always set this. If the state passed is 0, then we know that we are only calling this to get this requirement. Okay, and then we can take that requirement, allocate memory, and then call this again and pass that memory to state, right? In which case it would proceed beyond this. Okay, and in this case we're not actually doing anything fancy. All we do here is we'll basically say state pointer equals state, and then we'll set state pointer initialized equals to true, right? And this is kind of the flow that all of our systems are going to use. Okay, and so here is where we'd create the log file, right? So we wouldn't do that on the first initialize call, we do it on the second. Okay, so obviously since we have state here, we will also need to pass this in the shutdown. So in this case, all we're going to do is just unset the state pointer. So we're not actually going to do anything with the state itself, but we're just passing this here in case we need it for some reason. So here we just zero this out. Okay. And obviously we have some to-do items in here, so we may want to actually do that last. Next, I need to update the function signature on the in the header. So we have here our logger.h. So initialize logging, we have, oops, apparently I did not copy this. So I'll copy that, paste, and then void state here. Okay. And so here I'll just add a comment to this effect. So I'll say initializes logging system call twice, once with states equals 0 to get required memory size, then a second time passing allocated memory, I can't type today, memory to state. Okay, and then the size, actually a pointer to hold the required size of required memory size internal state. Okay, and then 0 if just requesting memory requirement, otherwise allocated block of memory. Okay, and then true on success, otherwise false, which actually there's a bug here that's going to get caught. This needs to be return true, not just return. Okay. Now, in application C, we need to update our call to this to actually handle this. So what we're going to do is for each one of our systems, we are going to basically add something to our application state that holds the amount of required memory as well as the actual state itself. So we have U64 logging system memory requirement. That seems kind of long, but that's fine. We're only going to be using it in one spot anyway. And then logging system state. Okay. And so for each system, we're basically going to have a set of these where we have the memory requirement and then a pointer to the actual state, or a block of memory for the actual state. Okay. So right here above, or in initialized logging rather, we're going to pass the address of state, app state, and then logging system memory requirement, and then we pass 0, right? So the 0 to the state tells it we only are looking for the size, okay? And here we're always going to return true, so I'm not actually even going to bother checking the result of that. Okay, so the next thing we need to do is we need to, whoops, I just realized there's a bug here. This should be linear allocate create, not allocate. I thought that looked a little bit weird. That would have been confusing. Okay, so we just need to change that to total size 0 and then a pointer to the allocator. Okay, or address of the allocator rather. Now we call linear allocator allocate. We pass it a pointer to the allocator, which is going to be this app state systems allocator, right? And then the size is going to be the app state logging system memory requirement. So this is basically where we get the memory from, right? And this returns a void pointer. So obviously we just assign app state logging system state equal to the result of that. Okay. So this asks for how much memory we need. This gets the actual memory according to the response from that. And then finally we call initialize logging again, this time passing the system state to state instead of 0. However, this time we probably should check to make sure that logging was successful. And if it is not, logging system shutting down. Okay. And whoops. And we will go ahead and return false in that case. Okay, so that actually resolves something that should have been done before. And this is basically the pattern that we're going to follow going forward, right? So all of our systems are going to be allocated this way. And this takes that state off the stack and gives us a more centralized location for it. And we can use void pointers here so that we don't have to have tons of cross dependencies between header files and knowing about those individual states across these different systems, because really the only place that should care about what the actual underlying type of that system is the system itself. So a void pointer should be more than adequate to actually accomplish that. So let's go ahead and fix all the errors in this, because we did change app state to a pointer. So I'm actually just going to do something that's probably a little dangerous, but I'm going to do it anyway. And search for app state dot and replace it with app state arrow. 41 changes. That looks like I got most of them. And then we have this initialized equals true, which we no longer have because we can check initialized to, just by checking to see if we actually have an application state. So if this guy is actually defined, then we can just use that. So let me go ahead and build. And run. Application failed to create. Called more than once. What did I do wrong? Oh, wait. Oh. Okay, I know what it is. So... Oh, that's fun. That's a logging bug issue. I'll have to fix that. So our application state actually has rubbish in there for its value because we did not zero out the game state, right? So it thinks that this has actually been allocated because this wasn't zeroed out, right? So I believe this might have been in the game itself, I think. In the game. Nope, that's not actually doing anything with it. Maybe it was entry. Yeah. So this is calling kallocate, which I thought actually zeroed out the memory for us. I wonder why that's not. Oh, right. Right. So we just need to do outGame application state equals 0. Right there. All right, so now we should be 0. So now we should be good. Okay. And we are back up and running. So, what we're going to do is we are going to basically implement this pattern for all of our other systems here. And that will allow us to sort of have a little bit cleaner of an implementation here. Now, this is going to get kind of repetitive, right? Where we have this sort of initialize double call here, and then allocate this. So eventually, probably what I'm going to do here is create an interface where I can just pass a function pointer for an initialize function, and turn this whole thing into a function where I can just pass a couple parameters to it and do it sort of in a loop. But for now, I think I'm just going to do this sort of repetitive for now, just to keep things simple. And if it grows to a point where I feel that's necessary, I'll go ahead and do that. Okay, so this is logging. One thing, I'm actually going to take these test logs here, and I'm actually going to take them out of here and put them in initialize logging, because this is actually technically where that test is being done anyway. So let's go ahead and put that there, get that out of application. And logging, probably, believe it or not, is probably not going to be the first one that we're going to do. There are going to be other systems that we're going to actually wind up doing as well. Okay. So let me just check the chat here. Watching you code, I feel stupid. I feel that same way about watching some other people code sometimes. So don't feel stupid about it. It's just, you know, we're all at different levels. As long as you continue to learn, that's a-okay. You know, you don't have to be at the same level as somebody else, right? There's always going to be somebody better, somebody smarter, somebody more skilled at it than you are, and that's okay. You don't have to be the best at what you do. You just have to be willing to learn and improve. Just submitted a small pull request for the Linux event loop. Okay, I will take a look at that probably after the stream. Just because I'm hoping to actually wrap this up. I actually have one more thing that I want to cover before we wrap up here. Just because of time, I'm actually not going to implement this for all the systems right now. I probably will do this off stream because I actually want to move on to something else. So the last thing that we want to cover is I want to put in some sort of tracking for dynamic allocation, but I also want to track dynamic allocations that have happened sort of after our initial startup phase, right? And then I also want to track allocations that happen every frame, because that is going to be incredibly useful for not only eliminating dynamic allocations in our game loop, but keeping track of how many we're doing overall. It's always just kind of a good thing to keep track of. So I'm going to go ahead and put that in place now. It's actually somewhat simple. So yeah. Our first modifications are actually going to be to our memory system. And something that I noticed is our initialized memory is actually being called here. And this is probably not the place to do this, because I'm actually thinking that this probably should really be done in the application, right? Even though, well, yeah. I mean, even though technically speaking, it needs to be done first and foremost, there are reasons that I'm going to have to move it to happen a little bit later than this, because I actually need something to happen before this, and I don't want to put that here. So I'm going to move this back to the application. So I'm going to put that actually before logging, right? And I think I do still have that there, so I should be good. Let me go back to the entry. Was it entry? Where was that? Yeah, entry.h. Shutdown memory. I need to get that out of here as well, which actually technically means I can get rid of that. Okay, so back in application. So I have the initialized memory here right below our linear allocator creates, and I'm actually going to go down here and after platform shutdown, put shutdown memory there. And I'm actually just going to build this real quick. See what it breaks. I'm pretty sure I had a reason for doing that. I just don't remember what it was. Okay. So it actually works. So I'm not actually sure why I had moved that. Because it seems to work just fine. So yeah. All right, so in application, we are actually going to have to change up the way that this state works a little bit, because as you may or may not have noticed, we have some static state here as well. We don't want this. So first thing is going to be type def struct memory system state, and it'll become apparent here in a couple minutes why I'm actually doing this. But let's go ahead and put the memory stats there in the state. We need a pointer to this, so we'll say static pointer to the state, and we'll call it state pointer. Right, we're just going to follow the same pattern as what we've done before. So we'll have a pointer to a U64, and we'll call this memory requirements, and then a void pointer for the state. Okay, and we will set the memory requirement equal to size of memory system state. Okay, same as before. If memory equals 0, return. Okay. Otherwise, we will go ahead and say that state pointer equals state. Oh, should be state, not memory. And then here we'll just point to state pointer Whoops, stats. Okay. And this should actually just be, yeah, we'll take the size of that. Okay. That, I believe, should be all that we need to do for initialization, at least for now. We also need to take the void pointer state here, just in case. For now, though, we're just going to unset the state pointer. Equals 0. Okay. And then, obviously, we'll have to take the state pointer and prepend that to anywhere that we're using stats. Just to fix all of those errors. Okay, and I think, and this is still kind of crappy, by the way. I'm probably going to refactor this sometime soon. I'm just not going to touch it today. All right, so that is our memory. So let me go ahead and change the application to do that. So let's actually take this and move it down here. Okay, so up here, we obviously need a new set of these. I'm going to put them at the top, try and keep them in the same order. I'll say memory, system memory requirement, and memory system state. And we will pass the address of app state, memory system memory requirements, and we'll pass 0 for the state, first time we call it. And then I'm actually just going to copy pasta this line and change this to be the memory system states and memory system state requirements. Whoops, that's here. Okay. And then we're going to copy this so we can call it again. And we'll pass the newly set state here. Okay. So let's build this real quick, make sure this works. And it does not. So what do we have? Right, this is why I had it moved before. Okay, now I remember. So this just needs a couple checks. Basically say, like, if we have an allocation that happens before all this stuff is stood up, which can happen, we'll say if state pointer, right? Because obviously this isn't going to work if we haven't stood up the memory system yet. So we'll just wrap that, and that should fix that. Okay, and now we're good. Okay, all right. Let me just check on the comments here. So sometimes it's not about being smarter, it's just that sometimes it's difficult to follow the thought process. Yes, that's absolutely true. And I've been programming for a lot of years, and that never changes. Who is the man in your avatar? That would be me, with considerably less fuzz and hair. Yes, a young hem. Yeah, that photo is probably 10 years old, or 11 years old at this point. No, 10 years old. I need to run. This was very informative. I really enjoyed it. See you next time. See you later, Giuseppe. Thanks for coming on board and hanging out with us. It's been great to have you here. All right. Okay, so now that we have that, we can go ahead and add in our tracking. So one thing we want to add to our state is we want to keep a running count of the number of allocations that we do. So every time we call kallocate, we're going to increment this counter, right? So I'm going to say u64 total allocations, or actually I'll just say alloc count. That'll work. And so when we set this up, we'll say state pointer alloc count equals 0, right? And then anytime we call kallocate, we're going to increment that. right? And that is for reporting purposes. So the other thing that I want to do is I want to expose a function to actually write that out. So I'll say u64. We'll say get memory alloc count, right? And this is just so that we can report from outside the application if we want to know this, which we'll be doing here in a second. So I'm going to go down to the bottom here, and I'll just put this here at the bottom. Oops, keep typing P. Okay, and if state pointer, return state pointer alloc count. Otherwise, we're going to return 0. Okay, that's just a simple way for us to sort of keep track of that. Okay, right. So for now, I think that's all we need to do in here. Our application is set up and ready to go. So now I'm going to head over to the game, and I'm going to add something into our game. So let's do it here. And in our game update, I'm actually going to add some code here. And this is not particularly game code, but it gives us a nice way to sort of be able to query for this whenever we want to do so. So what I'm going to do is I'm basically going to keybind one of the keys on the keyboard so that when the application's running, if I hit that key, it's going to query how many allocations we actually have, and then that can change over time. So with that, let's go ahead and see. I'm probably going to need, I think I just need input for this. So I'm going to add that. And then probably am going to I'll have a u64 alloc count equals, and I'm actually going to need memory as well. Okay, memory. Get memory alloc counts. Right. And I'll do this every frame. And I'm going to store this actually statically. So if you put static like this, it basically turns it into a static variable that is scoped to this function, right? Function call is not allowed. I don't know what it's bleeding about there, but okay. All right, so we're going to check if the input key is up, right? And we'll map this to M, right? So we'll say if the key is currently up, but the input key was down, right? So in other words, if we pressed it on a frame and we just released it, then we're going to do this, right? So we'll say, if that's the case, we'll say k debug, and we'll say allocations, and we'll pass in an LLU, which is just a 64-bit number, and then that'll give us the total number of allocations, and then we'll pass in another one where we'll say this frame. Okay, and so for this one, we will pass alloc count, and then we'll pass alloc count minus something called previous alloc count, which we haven't defined yet. And this is basically going to tell us the total number of allocations plus the number of allocations that have happened on this frame. Okay. Why is this bleeding? Previous allocation. Oh, okay, because of this. Okay, so previous allocation count. We're just going to put right here. We'll call that, we'll say that's a U64. And we'll say that is equal to allocation count, or alloc count, right? And then say alloc count is equal to that. So actually, I'm going to set this to 0. Initialize it to 0. Okay, that actually makes a little bit more sense. Okay, so the first time this runs, this will get created and statically set to 0. And then every update frame, we will have, we'll take the previous allocation count, which is the current allocation count, and then we'll get the actual allocation count from the memory subsystem and reassign that. And then here we'll take the difference between those, and that's how many actually happened this frame since the last update. And since this is called once per frame, that's what'll give us that. Okay. In kmemory.c, you miss a comma in the strings above. Yeah, I saw that there was something messed up in the text, and I was wondering what that was. I think you're probably right about that, so let me just look at that real quick. Yep. That would do it. Thank you for that. Off topic, but I think where do you set this frame buffer width and height? From either 0. Yeah, that's because we haven't actually hooked all that stuff up yet. 5 or 6 validation errors. Although actually, no, I think we actually did hook that up. But we have some defaults and stuff that we use. So if I have time, we'll circle back to that. Okay. So we'll run here, and now every time I press M, we see that we have 27 allocations. So since the state was actually started, we have 27 allocations, and we don't have any actually showing up in per frame, but it's kind of a nice way for us to be able to tell if we have stuff being allocated every frame, which eventually we might. So anyway, now that that is hooked up, that just kind of shows an example of one way to monitor that kind of thing. I just want to add that there. Now that that's hooked up, I think this is probably where I'm thinking of ending. Because there is actually some other stuff that I want to add in here, but frankly, my voice is getting kind of tired. So do you guys have any questions aside from the frame buffer thing? And I'll get to that in a second. And while I'm waiting for input there, I will jump into the Vulkan backend. So you're wondering about the frame buffer width and height. So there's this cached frame buffer width and height that are set here. And then I have in initialize, I'm actually calling the application get frame buffer size. And then that is taking pointers to those two. And then this next line basically checks to see if those things are 0. And if they're not 0, it uses that, or otherwise it uses the default of 800 by 600. And then when we call on resize further down, I think actually that's done at the application level. Let's see. I think that is done at the application level. Right here, we call this once manually after the window has been launched to actually sort of make sure that that's the right size. So I'm not sure if that's what you were asking. Yeah, I think I covered all of this in that episode. Or if not, I might have touched on some of this after that. if there was part of it I missed, I can't remember, to be completely honest with you. But yeah, it's all of this is definitely covered in the series. Okay. Okay, cool. Yeah, I think that is probably all I am going to cover for now. I think this has been a decent stream. I think we covered a lot of ground. There was a lot of explanation. I don't feel like we wrote that much code, but I feel like we've got some nice tools in here to be able to build on top of. And so as far as the rest of these other subsystems and switching over to this new memory model, I'll probably go ahead and do that off camera and sort of silently push it to the repo, and then after that I'll maybe mention it in the next video in the series. So okay, cool. Well, thank you guys so much for tuning in. I really appreciate all the interaction and feedback. This has been a lot of fun. I wish I could do this more often, but unfortunately I don't have a stable enough schedule to allow it. Real life gets in the way a lot of times, so I'm not able to do this as often as I would like, but who knows, maybe down the road. But if you guys like this, feel free to toss me a like on it and let me know that you guys liked it, and feel free to leave me any feedback in the comments once this is switched over to a just a regular video. And if you haven't already, feel free to subscribe and pass it on to your buddies and whatnot. If they're interested in programming or game engine development, I'm going to keep this running for quite a while. So I can't think of anything else other than, oh, actually there is one other thing, because I haven't officially mentioned this on stream yet, but there is KohiEngine.com. I don't know if you guys have all seen this yet, but it's a new website that I launched, sort of giving a little bit of information about the website, or about the engine rather, and some links to the various things, like getting to it on YouTube, joining our Discord, contributing on the GitHub, of course a link to Patreon if you guys want to support me. I appreciate that, as well as some of the latest videos that are here available. And then there's also some frequently asked questions here available about the project, and then the community just takes you to the forum, which I launched not too long ago. So I'll probably continue updating this, but just letting you guys know it's there. So cool. All right, well, thank you guys, and I will see you guys around. I think that is basically all I'm going to cover for today, so I appreciate you guys showing up, and until next time, keep coding.